Um, so the next two talks will be a series on the mean curvature flow in R3 and the multiplicity one conjecture, given jointly by Richard Bamler of UC Berkeley and Bruce Kleiner of Koran Institute. And our speaker will clarify who he really is.
Okay, so first, I'm not Richard Bemler. So thanks to the organizers for inviting me to speak here. It's certainly an honor and a pleasure. Happy birthday, Tian. And I'd like to thank you for all your brilliant and inspiring mathematics over the years, and also for your many outstanding students. It's been a pleasure to interact with over the years. So I'm going to be talking about mean curvature flow, mostly restricting to the case of surfaces in R3. When I get to the new results, this is joint with Richard. Let me just start with some definitions. Of course, Brian already covered this, or some of this yesterday, but let me go over this quickly, right? So if you have, say, a smooth family of submanifolds of Rn, okay, parameterized by T lying in some interval I, we'll think of that as a manifold that's evolving in time. And then that's a mean curvature flow if its velocity equals its mean curvature. Okay? More explicitly, you think of the velocity of this moving submanifold as a normal vector field along the submanifold, and that should be equal to the mean curvature vector field, which is another normal vector field, right? So another way to think about that is in terms of parameterized submanifolds. So then here you have a family of mappings, say Ft, of some fixed abstract manifold n into Rn. Let's say these are smooth embeddings. And then this is a mean curvature flow if the time derivative is equal to the Laplacian, okay? With a caveat here, the Laplacian, this delta t refers to the Laplacian associated with the metric you get from Rn by restriction at time t, or you pull back the Euclidean metric using Ft and look at the corresponding Riemannian Laplacian, okay? So these two notions are equivalent. If you look at the image of this parameterized guy, that will give you a mean curvature flow in this sense here. Okay? So another take on this is in terms of graphs. So let's say we're in the codimension one case. You have an evolving hypersurface. Locally, it's the graph of a time-dependent function ut. Here, this is defined on some, say, open subset of Rn minus 1. Right, and that the graph of this time-dependent function will be a mean curvature flow if and only if the ut satisfies this PDE. It's a quasi-linear parabolic PDE, this linear combination of second derivatives, okay, where the coefficients depend on the first derivative. Okay. Now, another view is that the mean curvature flow is a steepest descent evolution, right? So you think of the space of all submanifolds of Rn, and you think of that as some sort of formal infinite dimensional Riemannian manifold with the L2 metric, and then this is a gradient flow, right? So this is basically a reinterpretation of the first variation formula for area. If you look at the variation of area of the submanifold in the direction of a variation vector field C, right? That's equal to the interval. So you take the inner product of the variation vector field of the mean curvature, integrate it with respect to area, or the minus sign, and this formula just exhibits minus h as the formal gradient of area. Okay, so if you move in the direction of h, right, that's kind of the steepest descent evolution. A little history. So mean curvature flow first showed up in the literature in the 1950s in the physics literature. This was in connection with annealing. But mean curvature flow is a natural mathematical model for lots of different physical situations. In general, if you have a surface or an interface and the energy is proportional to area and you can neglect inertial effects, well then mean curvature flow is the mathematical model for that. So from a physical point of view, this is just the first of a long list of more and more complicated mathematical models where you add back in different, different forces or different effects, okay? So, all right, now within mathematics, mean curvature flow is useful as a tool. You can use it in various topological problems, geometric problems. You can use it in, say, general relativity. You can use it to produce nice foliations, minimal submanifolds, and so on. From the point of view of PDE, we already saw that the mean curvature flow is a kind of version of the heat equation, right? So it's one of a small list of, say, fundamental geometric partial differential equations, right? So it's a natural analog of the heat equation for an evolving surface, and it's also a parabolic analog of the minimal surface equation, okay? Now, in the mathematical community, mean curvature flow has been studied quite heavily since the late 70s, since fundamental work of Brocchi in 78, and people are coming at it from different points of view. There are kind of different groups of mathematicians. People have used different tools, geometric measure theory, classical differential geometry, and conventional, sort of traditional PDE techniques. Okay. All right, so back to the thread. So I'm going to be sticking almost exclusively to the case of surfaces in R3, but some of what I'm going to say holds for hypersurfaces in higher dimension, and some of it's even in hard codimension, but mostly it's surfaces in R3. So let's start with some special solutions. So the simplest one is just a static plane. You just take a plane that just sits there, right? That has curvature equal to 0, mean curvature is 0, so that's a solution. The next generalization of that is a static minimal surface, a minimal surface that just sits there, since a surface is minimal if and only if the mean curvature is 0. So maybe the first interesting example is the shrinking round sphere. All right, if you have a round sphere, the mean curvature points inward, so it tends to shrink. That makes the curvature gets bigger, so it shrinks even faster. And you get a solution by taking a sphere centered, say, at the origin. Radius at time t is given by square root of 1 minus 4t. So that starts with radius 1 and goes to radius 0 as you approach t equals 1/4. So variation on that is a shrinking round cylinder. You take a circle centered at the origin in the plane, cross it with r, so this gives you a round cylinder. You take the radius to be 1 at time 0, then at time t it will be square root of 1 minus 2t. So that round cylinder collapses to a line as time approaches 1/2. Some general properties. So short time existence and uniqueness. Right, so this follows from classical methods. So if you have a compact smooth surface in R3, well, then you have a unique solution to the mean curvature flow equation. So this is a unique mean curvature flow. It's defined on some time interval 0 to capital T, where the initial data is equal to n, right? And this is the maximal interval of existence. And the assertion is that, in fact, this time capital T is finite, so it's only the maximal solution is only defined on a finite time interval. And in fact, the second fundamental form, which I'll be denoting by A, this blows up as you approach this time capital T. So this is what we saw already in the case of the shrinking sphere that shrinks down and the curvature blows up on the maximal time interval. So an important property of mean curvature flow is avoidance. So if you, let's say you have two mean curvature flows, M and M prime, so these guys are, say, compact smooth surfaces or evolving surfaces. So if they're initially disjoint, so their intersection is empty at the initial time t1, well, then their intersection remains empty later. So if they're initially disjoint, they remain disjoint. So this is an easy consequence of the maximum principle. And a variation on that is kind of self-avoidance that says the surface, mean curvature flow can't kind of touch, you can't have two different mean curvature flows bumping into each other. You also can't have a surface, a single mean curvature flow bumping into itself. You can formalize that as follows. Right, if you have a mean curvature flow with uniformly bounded curvature, right, it's defined on a half open interval 0 to t0. And if it happens, right, so curvature remains bounded as you approach the right endpoint, well, then in fact this surface has an embedded limit at time t0. Okay, so this fact is kind of implicit in this formulation of the short time existence. Okay, let me say where I'm going. So just a glimpse. So I'll start with a little bit of phenomenological discussion, looking at some special cases and special solutions. That's going to draw attention to what happens at this blow-up time. So we want to understand blow-up. That leads to focusing on the formation of singularities, looking for what might happen. And then after that, I want to discuss what happens when you try to flow past singularities, flow beyond singularities. Okay, so that will be the last part. All right, so the simplest case is probably to drop one dimension. Let's go from looking at surfaces in R3 to looking at curves in the plane. So that's the mean curvature is just the geodesic curvature, and mean curvature flow in the plane is usually called curve shortening flow. So here the beautiful theorem of Gage, Hamilton, and Grayson is the following, where you have a curve shortening flow in the plane whose initial condition, M0, is connected, just a nice smooth, simple closed curve, right? Then what happens as you approach the blow-up time is that the curve converges to a point. So Hausdorff converges to a point, and it becomes asymptotically round, meaning modulo an appropriate translation and dilation, the curve will converge smoothly to a round circle as you approach the time capital T. Okay, so this is kind of a beautiful, beautiful result. Now let's go back to R3. So Huysken showed that you have similar behavior if your initial condition is convex. So you take a compact convex surface, take that as your initial data. Well then, as you approach the blow-up time, the surface shrinks to a point and becomes asymptotically round in the same sense. Now, if you drop the convexity condition, the behavior gets more interesting. For instance, if you take a thin torus of revolution, right? So you take, let's say, a circle in the right half plane and then revolve that around the z-axis. So if you take that circle so that the radius is small compared to the distance to the z-axis, kind of thin torus of revolution, at any point on the surface, there will be two principal curvatures. One will be large and will kind of point inward, and the other will be moderate. Sum is going to be the mean curvature, which will be large, pointing inward, and that will make this torus of revolution shrink. It remains a surface of revolution, so one can show that in this case, what will happen is that this thin torus of revolution will evolve and collapse to a circle. Okay. Now, another key example is a Dumbbell example, which gives you a neck pinch. So here, you have a surface, right, which has two roughly spherical portions joined by a neck. And then under the evolution, the neck again starts getting large mean curvature. It starts shrinking rapidly, and this instability leads to this kind of neck pinch, right? So from these three examples, I want to point out that in the first one, right, the surface shrinks entirely to a point. So there's just a singular point, and the surface shrinks down to it. In the second one, again, the whole surface kind of disappears, but the singular set is not a point; it's a circle. Okay, and in the neck pinch case, there's again only one singular point where this neck pinch occurs. However, unlike in the two previous cases, there's some surface left at the blow-up time. In fact, you can show that away from the singular point, the flow actually has a smooth limit. So you have this smooth limit surface left over. Okay. So now a natural question is sort of how can you understand these singular points? So the strategy is to use blow-up. Okay. So this is based on a symmetry of the equation. Of course, if you have a mean curvature flow, you translate it or you rotate it, you get another mean curvature flow. But you can also rescale the mean curvature flow and get another mean curvature flow, provided you scale space by one factor and time by that factor squared. Okay, so here, if you start with a mean curvature flow and choose some fixed positive number r, So then you scale the time slice by R inverse and scale time by R squared, you get another mean curvature flow. Right? Now, the space-time view of this is as follows. It's useful. So let's look at the space-time track. For every t, you take the surface at time t, you cross it with the singleton, and then, right, so it's just sticking the surface at time t in space-time and take a union over t. This is the space-time track. So then, right, if you apply parabolic rescaling to that space-time track, you get the space-time track of another mean curvature flow. Okay, so you map x comma t to r squared t. So that's just a restatement of what I have up here. Okay. So, right, so let's think about how this works in the case of the neck pinch that we were just looking at, right? So suppose the neck pinch occurs at x0 at time t0, okay? So let's translate things so that x0 becomes the origin and shift time so that t0 becomes 0. So after we do that, then we start doing the parabolic rescaling, and that leads to this family of mean curvature flows depending upon a choice of r. And you can show that this family of flows actually will converge to a very simple flow. It will converge to a shrinking round cylindrical flow as r goes to 0. And because of the time shift, this limiting flow is defined for negative times, defined for t less than 0. Okay. So in terms of the picture, if you look at if you do this space-time shift and this rescaling, and you look at the time minus 1 slices, this is what you see. Okay, becoming cylindrical. Okay, so let's try to generalize the example of the shrinking round cylinder. So this leads to shrinking solitons, because Brian was talking about translating solitons yesterday. All right, so a shrinking soliton, so up to space-time translation, a shrinking soliton is a mean curvature flow that looks like this. So it's defined for negative time. And at time t, you just see a fixed surface rescaled by square root of negative t. All right. And equivalently, that's you're just saying that this surface, the time minus 1 surface, which is n, that satisfies this elliptic PDE. So the mean curvature vector is equal to the following. X is the position vector, so you take -1/2 that and take the orthogonal projection to the normal space. That should be equal to h. All right. So we already saw examples of shrinking solitons. So we already saw the shrinking round spheres and shrinking round cylinders. So those are shrinking self-similarly. So Angenent discovered examples of tori, which, unlike the marriage ring collapses to a circle, right? The Angenent tori shrink in a self-similar way and collapse to a point. Okay, so those were discovered a long time ago. Much more recently, there have been many more examples constructed. So, for example, Capellas, Kleinmuller, and Nguyen produced shrinkers of arbitrarily large genus. So these look roughly like this. So think of a plane passing through the origin and then the sphere of radius 2. So those two surfaces intersect along a circle. So if you look at the circle of intersection, you zoom in, and infinitesimally you see two planes intersecting orthogonally. And these examples you can think of as being constructed by desingularizing that along that curve by inserting a Shirk second surface, surface approximated by Shirk's second surface. Okay. So any such shrinker can potentially arise as a singularity, the way that the shrinking round cylinder modeled the neck pinch singularity. Okay, and so there have been many examples constructed, and so I think Brian already mentioned this, that there doesn't seem to be any hope of classifying shrinkers. There are lots of them, and they all potentially serve as models for singularity formation. Okay. Now let's shift gears. So now these shrinking solitons serve as potential models for shrinkers. You can ask, well, does that exhaust the possible behavior at blowup? Okay. So this leads you to singularity analysis, and here the philosophy is the same, is analogous to the idea of that comes from looking at singular minimal surfaces. You use the monotonicity form. If you have, say, a minimal, stationary minimal integral current or stationary varifold, you have a monotonicity formula. And using that, you can show that if you have a singular point, then on magnification, your surface will converge subsequently to a cone, a minimal cone. All right? So, the same idea can be implemented, or you can try to implement it for mean curvature flow, and this was done by Huisken. So that looks as follows, right? So you take some base point in space-time, so x0, t0, and then you look at this kind of backward heat kernel, right? So it's kind of a backward heat kernel centered at this point in space-time. So with the caveat that it's not quite the 3D backward heat kernel, it corresponds to a two-dimensional heat kernel, which kind of makes sense since we're going to be integrating it over the surface. And so Huisken's, so if you give yourself a mean curvature flow here, mt, so then you can look, Huisken defined the Gaussian area at some time t strictly less than t0, right? T0 is our time base point. As follows, you just take this kernel, integrate it over the time t surface with respect to area, okay? So that's our theta sub x0, t0 time t, and Huisken proved that this is monotone. So if you look at the Gaussian area at the later time, it's less than or equal to the Gaussian area at the earlier time. And if equality holds, then you have a shrinking soliton, okay? So, I mean, this is based on a calculation that shows the time derivative of the Gaussian area is less than or equal to this integral formula. So it has a sign, so we're integrating against this kernel, which is positive. So if this quantity vanishes, well then the integrand vanishes, which tells you have a shrinking soliton. Okay, so so this implies in particular that you have a well-defined density. So this thing has a well-defined limit. If you fix the point in space-time, then this has a limit as t approaches t0, which is the density of the mean curvature flow at that point in space-time. And now this leads us to look at the analog of the tangent cone for minimal submanifolds, and that's these are the blow-ups or tangent flows. Okay, so let me go through this. So you have, let's say you have a smooth mean curvature flow blowing up at time t, capital T. So if we choose a time strictly smaller than capital T, right? So we look at the smooth mean curvature flow before it blows up, and you choose a point x0 on the t0 slice, right? So then this Gaussian thing is going to concentrate down on the smooth point in the flow, okay? And it's not hard to convince yourself that since this corresponds to a two-dimensional Gaussian, then in the limit, the density is going to be equal to 1, okay? On the other hand, if you take t0 to be the blow-up time, you might have a singularity forming near this point in space-time, and then the density could be strictly larger than 1, okay? So another feature of this is that the Gaussian area, it's easy to check, it's actually invariant under parabolic rescaling. And so what that implies, right, is that if you look at this family of rescalings that I discussed before, you choose a point in space-time, you translate it to the origin in space-time and start dilating, the guys that you see will have Gaussian area that's closer and closer to the Gaussian density of the mean curvature flow at that point in space-time. So these guys have kind of asymptotically constant Gaussian areas, R goes to 0. In particular, right, as a consequence, any subsequential limit of this family, right, the family has asymptotically constant Gaussian area. So if you have a subsequential limit, then that will have constant Gaussian area, okay? So by Huisken's result, that will be a shrinking soliton. And such a thing is called a tangent flow of this mean curvature flow. Now, Ilmanen showed that actually you can extract such a subsequential limit. So he has an important theorem from 1995. So he showed that this, if you look at this rescaled family, well, it does converge subsequently to a smooth shrinking soliton, okay? But there are two caveats here. First, this is not smooth convergence, okay? So it's a kind of a weak convergence. So what's happening is instead of looking for each R, you have a mean curvature flow here. So instead of looking at the evolving surfaces, you replace the surfaces by the surface area measures. Okay? So you get an evolving, for each R, you get an evolving measure. And then the claim is that that family of evolving measures converges weakly in a natural sense to an evolving measure. And the evolving measure is going to be the surface area, surface area measure of this shrinking soliton, possibly multiplied by some integer, which might be larger than 1. Okay? So that's there are two caveats, right? One is the convergence is not smooth, it's some sort of weak convergence. And second, this weak limit is not the area measure, not necessarily the area measure of this smooth shrinking soliton, it might be some integer multiple. Okay? So Illman emphasized here, right, that the reader should be aware that the convergence to the blowup might not be smooth, so there might in principle be small necks in other topological kinks that pinch off and disappear in the limit. Right? So that was consistent with what he was able to prove, but at the same time he conjectured that the shrinker limit actually had multiplicity 1. So this is the multiplicity 1 conjecture, and in fact, if this conjecture is true, that it implies that this kind of pathological behavior does not occur. In fact, the convergence is smooth convergence. All right. So our first result is that this multiplicity 1 conjecture is true. And now I want to shift gears and talk about, in the few minutes that remain, talk about mean curvature flow through singularities. So here the idea is given by this cartoon, right? So we take what we had before, the neck pinch occurs, but we kind of want to keep going and have some continuation of this, which is some sort of flow, mean curvature flow through singularities. Okay? So before going further, let me just mention the motivation. So first, from a PDE viewpoint, it's natural to expect some sort of theory of weak solutions or generalized solutions, just as you have the notion of stationary varifolds or stationary integral currents. In the case of minimal surfaces, there are weak notions of harmonic maps or harmonic map heat flows or Navier-Stokes, et cetera, right? So this is a completely standard agenda. Also, if you're interested in mean curvature flow as a mathematical model, well, physical systems like soap films and so on evolving, they have neck pinches and they continue flowing. So certainly you want to have a mathematical treatment of that. And then also just within mathematics, most potential applications of mean curvature flow can only be given if you can flow through singularities. If you have to stop when a singularity forms, it's kind of useless. Okay. So what happened, right? So the goal was basically to develop some notion of a flow through singularities, and over time, people formulated conjectures about what this should look like. So some of these were folklore, some of them appeared in the literature, maybe in slightly different forms. But let me say what they are. So the first one I'll call existence and regularity. So the assertion is that there should be a flow through, mean curvature flow through singularities where the singular set is not too big. Okay, so this is some kind of tameness condition. So here we're saying that the singular set should be contained in spacetime, should be contained in a finite collection of curves. So if you think about the examples we've already discussed, right? I mean, the neck pinch and the convex case, there was only a single singular point. Then there was the marriage ring, which had a curve of singular points in space-time. And people have come up with other types of scenarios, imagining what might happen, but none of them involve a larger singular set than that. Okay, so that's the first motivation for the first conjecture here. And then the multiplicity 1 conjecture is really an enhanced version of what Illman conjectured. Illman's conjecture concerned the behavior of a smooth mean curvature flow at blow-up time, and so this would apply even after blow-up. Okay, and then there are various conjectures about what should happen if you're allowed to take a generic initial condition, right? So maybe if you choose the wrong initial condition, maybe some complicated singularity could form, like the one that I showed before with high genus. But if you're allowed to perturb the initial surface, or if you're looking at a generic initial condition, then maybe the behavior is quite a bit simpler. Okay, so from the PD viewpoint, this is actually a broad agenda. People look at generic solutions to PDs, whether they're plateau problems or generic solutions to evolutionary PDs with generic data. But in this context, one version of this is due to Huysken, which says that for generic initial data, the singularities, so the tangent flows, should be round spheres and cylinders. Okay, so none of these complicated shrinkers should arise. And then, so Brian has a conjecture that, so if the initial condition is topologically a two-sphere, so then actually the flow is unique. And moreover, the singularities are simple, just as in the generic case, they should be modeled on shrinking round spheres and cylinders. So this conjecture was motivated by an example of Illman and White showing that the uniqueness can fail for high genus. Okay. So I should mention that these are not really mathematical conjectures. They're not coherent because, right, I'm referring to a flow here, but I haven't said what the flow is, right? So you should think of this maybe as kind of a mathematical physics project, right? You're trying to produce some kind of object which meets this set of specifications, right? In any case, this describes a big part of the research agenda in mean curvature flow for quite a while, and so we can now address all of these in the case of surfaces in R3. Okay, so Richard will talk about that, and I'll stop there.
Any questions for Bruce?
Do you all expect to classify like compact self-shrinkers, since like most of the examples that were given were like they're known to be or thought to be non-compact?
Yeah, let's see. I think for high genus, there's not really any hope. I mean, I'm not aware of anybody being hopeful about it. It's like trying to classify. Could be compared with a project of classifying minimal surfaces in R3. Right?
Okay, sure.
Finite genus there.
Theorems, the mean convex case, and then the genus zero case. There's the other classification can be done, but otherwise, yeah.
Yeah, so Brian is pointing out if the initial condition is mean convex or as genus zero, then you have a good understanding, but otherwise, yeah.
You mentioned looking at the space-time track of the mean curvature flow. Have you calculated the actual space-time curvature? Perhaps it's a Ricci flat metric, in which case it might be an empty space-time in the sense of relativity.
Yeah, it's not usually.
But do you know what the curvature is?
I'm sorry?
Have you calculated the space-time curvature of the space-time track?
No. I mean, not in general.
And the reason I mention that, of course, in relativity, there are many ways to handle singularities, so you can flow through singularities. Every time there's a black hole, you have to flow through the singularity. So perhaps those methods could be brought to bear once you know the space-time curvature of the space-time track. Just a suggestion.
Thank you. Thank you.
I think in the case of rich flow in 3 dimensions, Perelman's way is not going to singularity, but just to surgery slightly before. Are there people who is working on that kind of approach in mean curvature flow?
You mean flowing through singularities?
Yeah.
No. Not since Richard and I did it a few years ago.
Why? Are there some difficulties? Or?
That was a previous project that Richard and I did.
Sorry, yeah.
Yeah.
Sorry, I couldn't hear it. Yeah.
Any other questions? Questions from online? Actually, I have a question. Can we look back at an example of multiple genus? That's a, okay, so this is a soliton, right? Right. Can it occur as a singularity model?
So I believe I have not found in the literature a result which would quite prove this. Maybe somebody else is aware. But I mean, the expectation would be if you have a, say, a shrinker with a conical shrinker, I mean, a shrinker with conical ends or cylindrical ends, that it would arise. The analogous statement for Ricci flow is known as of a few years ago. For Ricci flow. I'm not sure. I thought it was Ricci flow, but I mean, certainly one would expect that, but I don't think that, I'm not sure, but I don't think it's in the literature for mean curvature flow.
Okay, thank you. Well, if there's no other questions, let's thank Bruce again.